Hi class, in this lecture here what we want to do is we want to start talking about basic differentiation rules, and there's going to be a lot of rules in this lecture and a lot of examples. So, have your notes ready as we work through them. When I put up a problem, consider pausing the video and, trying to solve the problem and then unpausing it and seeing as how I work the solution. Okay, so what we're going to complete in this section is the following. We're going to find the derivative of a function using many different rules of differentiation. Okay, we're going to talk about something called the constant rule, the power rule, the constant multiple rule, and the sum and different rules. And then what we're going to do is we're going to talk about how you find the derivatives of the sine and cosine functions. And I'm going to do an informal proof of that for you, for one of them. And then we're going to talk about how you find the derivatives of exponential functions, specifically just this function, e to the x. Okay, we'll talk about in later lectures on, we'll talk about how you find the derivatives of other bases that are not e. But this one here, we're just going to stick with e. Okay, so in the previous lecture, this is what we did. We used the limit definition to find derivatives. So for example, one of the common problems we worked, right? F of x was equal to x squared. And we said, okay, well, f prime of x was equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Well, in this case, what it was the limit as delta x goes to 0 of x plus delta x squared minus x squared all over delta x. And I'm not going to redo the problem because that's in the lecture, right? The previous lecture before this. And what we saw, this was really important. What we saw was that this limit was equal to 2x. And so what I want to do in this lecture and in other ones that follow this is we're going to introduce several differentiation rules that allow us to find derivatives without the direct use of the limit definition, so that we can just find, like, maybe there's a shortcut way. So, all these differentiation rules are going to be shortcut methods. So shortcut methods for finding the derivative. Okay, just these shortcut methods for finding the derivative. And we're going to use these rules every single lecture from here on out. So it's important that we have a good, deep understanding of all the rules. Okay, so the first one's the easiest one, and it's the constant rule. And so the derivative of a constant function is 0. Okay, so that is if c is a real number, and I say the following. Find the derivative with respect to x or any variable of some constant. It's always equal to 0. So notice that the constant rule is equivalent to saying that the slope of a horizontal line, right? Because that's what a constant function is. A horizontal line is 0. Okay? So this just demonstrates the relationship between the slope and the derivative. So it doesn't matter what the constant is. So here's some examples, okay? If I asked you to find the derivative with respect to x of just the number 4, so any constant, it's just 0, okay? Or if I say, what's the derivative with respect to theta of negative pi over 2? Well, negative pi over 2 is just a constant. It's 0. Or even if I say something like this, find the derivative with respect to x of e squared pi to the 4th, whatever. If it's just a constant, doesn't matter if it's, a whole number like this, or involving pi or e squared here, whatever. As long as it's a constant, the derivative of a constant is always 0. It's always 0. So that's really easy. So in the examples that we do later on in class, or in this lecture, I mean, whenever you see and have you seen me take a derivative of a constant, boom, it's just going to be 0. It's just going to, it'll just be 0. Okay, the most important rule today in this lecture here is the power rule, okay? So if n is a rational number, okay, so remember what a rational number is, it's like a fraction, right? Something like a over b. Then the function, f of x is equal x to the n, excuse me, is differentiable, and the derivative with respect to x of x to the n, look what happens here. You bring the exponent down in front, excuse me, and then you raise x to the n minus 1 power. Okay, so bring an exponent down in front. And the new exponent is n minus 1. That's it. Okay, it's really, really easy. Okay, so for f to be differentiable at x equals 0, right, n must be a number such that x to the n minus 1 is defined on an interval containing 0. So that means like, you just won't ever get a divide by 0. So this rule might seem a little weird at first, but after you see the first example or two, it's going to make perfect sense. Okay, so let's do some examples. All right. So in each of these examples, what we want to do is we want to find f prime, so the derivative, of each of the following. So he'll be the first one. F of x is equal to x squared. Well, look, we know, right, just going back, right, we know that this answer should be 2x. Okay, so whenever you have x to the n, okay, you can just immediately use this power rule. So here's what you're going to do. F prime of x. You bring the exponent down in front, and then you take whatever the exponent is, and you subtract 1. So this is 2x to the first power, or just 2x, so it works. It works. So if you have something like this, f of x is equal to x to the fifth power. So again, just follow the rules. F prime of x. You're going to bring the exponent down in front, and then you're going to have 5 minus 1. Well, that would be 5x to the fourth. So very simple. It's very simple when these exponents are whole numbers like this. So let's take a look at this one. We'll try to mix it up a little bit. Let's look at f of x is equal to the square root of x. It's like, oh, well, you know, maybe I can't apply this power rule now. But wait a second. Can you rewrite the square root of x as x to the 1/2 power? Yes, absolutely. So then all you can do is just apply this power rule. So the derivative, f prime of x. Take the 1/2, bring it down in front, and then you have x, and then you're still going to take this and go 1/2 minus 1. Well, 1/2 minus 1 is minus 1/2. So this ends up being 1 over 2 x to the 1/2 power, or 1 over 2 square roots of x. And then if you want, you can even rationalize the denominator, right? As like this. All right, but most common way you'll see it will either be like this, or they'll even leave it like this, which is totally fine. Or let's try this one. F of x is equal to 1 over the third root of x. All right, so you have to figure out how to rewrite this so that you can use the power rule, right? Well, look, you can bring this up, right? You can rewrite this as 1 over x to the 1/3, right? Just rewriting the third root as 1/3, which is the same thing as x to the minus 1/3. So then f prime of x. Bring the exponent down in front. So minus 1/3 x to the minus 1/3 minus 1. Well, minus 1/3 minus 1 gets me minus 4/3. All right, now let's just try this last one here. Let's look at f of x is equal to 1 over x. So look, the key here, is look, you just have to rewrite this so that you can use the power rule. So I'm going to rewrite this as x to the minus 1. Well then look, f prime of x is equal to, bring the exponent down, minus 1, x to the minus 1 minus 1. So this is minus x to the minus 2, or just minus 1 over x squared. So the key here is whenever you have something involving, you know, a radical or a rational function that just has x down there by itself, just rewrite it so that you can use the power rule. Okay, so I'll even highlight that up here. The key is rewrite so you can use the power rule. All right, let's move on. So the next is the constant multiple rule. And this is if f is differentiable function and c is any real number, then c times f is also differentiable. And, well, look, basically what this is saying is you can take the c, if you want to think about it like this, you could factor it out and then find the derivative and then just multiply the derivative by c. Okay, so if you have a c in front, some just, constant, just multiply it. That's all you need to do. All right, let me show you this with some examples here. So just some examples using this constant multiple rule. So again, let's just find the derivative of the following here. So find the derivative of the following functions. Let's look at this one. F of x is equal to 3x squared. Well, look, we know the derivative of x squared is 2x, and I have this 3 in front. So literally, just leave the 3 there, and then find the derivative of x squared. We'll bring the 2 down, and then I have x to the 2 minus 1. Well, what's 3 times 2? It's 6. 2 minus 1 is 1, or just 6x. So you're just multiplying the constant in. That's it. Okay, nothing special. So let's take a look at this one. Let's look at f of x is equal to 5 over x to the 2/3 power. Well, look, rewrite it. Write the key. Rewrite this, bring this up with a negative exponent. So it's 5x to the minus 2/3. So when you go to find the derivative, f prime of x, leave the 5 alone. Now just find the derivative of x to the minus 2/3. Bring the exponent down. And then subtract 1 from it. Well, 5 times minus 2/3 gets me minus 10/3. Minus 2/3 minus 1 gets me x to the minus 5/3. Which you can even rewrite as negative 10 over 3x to the 5/3. So look, the key is just treat the constant as a constant. That's it. We're going to do more of these, but let me just do this one. Let's look at y is equal to 6x. All right, well, when there's nothing here, there's an invisible 1, right? So look, the notation when you have y, it's dy dx, that's the derivative. So this is the alternative derivative notation. Is equal to, leave the 6 alone, 6, bring the exponent down, 1, and then you have x to the 1 minus 1. Well, 6 times 1 is 6. 1 minus 1 is 0. Well, x to the 0 power is 1. So this is just 6, right? That's what we would expect, right? Because it's just a straight line, so the slope is 6. So whenever you see the x there, okay, just realize, like, look, you're going to see me as we do some, later on lectures, I'm just going to say, okay, the derivative of x by itself is just 1. So if it's 6x, then the derivative is just 6. So you might see me, skip ahead a little bit on some of these problems when I do those. So just keep that in mind. Okay, the next is the sum and difference rules. Okay, so the sum or difference of two differentiable functions, f and g, is itself differentiable. Moreover, the derivative of f plus g or f minus g is the sum or difference of the derivatives. So look, it's just saying, look, if you take the derivative of f of x plus g of x, that's just the derivative of the first function plus the derivative of the second function. That's it, okay? Or the same thing with the subtraction. We take the derivative with respect to with respect to x of f of x minus g of x, that's just derivative of the first function, minus the derivative of the second function. And it's very, very straightforward. And you can expand on this if you have 3 terms or 4 terms or 5 terms in your function, whatever. Just take the derivative. Basically what this is saying is just take the derivatives of each term in your function or your expression. All right, let's do some examples of this. So again, let's find the derivatives of the following functions. So here'll be the first one. Let's look at f of x is equal to 4x squared plus 8x. So the derivative, f prime of x. Look, all you're going to do is you're going to differentiate term by term within the function. That's it. That's all the sum and difference rule says. Okay, so take the derivative of 4x squared, excuse me. Bring the 2 down. 2 times 4 gets me 8. X to the 2 minus 1 is 1, so that's just x. Plus the derivative of 8x, well remember, the derivative of x is just 1, so 1 times 8 gets me 8. That's it. Let's try this one. Let's look at f of x is equal to 2x minus 1 over the square root of x plus 5 over the third root of x. Well, look, what did I say the key was here, right? The key is you got to rewrite this so you can use the power rule. So this is 2x minus x to the minus 1/2 plus 5 x to the minus 1/3. So now when you go to find f prime of x, derivative of 2x is just 2 minus, bring the 1/2 down, so minus 1/2 comes down, x to the minus 1/2 minus 1 plus 5, bring the minus 1/3 down, x to the minus 1/3 minus 1. So this becomes 2 negative negative plus 1/2 x minus 1/2 minus 1 is minus 3/2 plus, well, forgive me, a negative. So 5 times minus 1/3, excuse me, is a minus 5/3. And then this is x to the minus 4/3. So again, the trick was just rewriting it. You had to rewrite it so that you could use it. All right, let's try this one here. Let's look at f of t now. F of t is equal to t cubed minus 2t squared plus 7 all over t squared. So it's like, oh, what are we going to do to solve this one, right? I haven't talked about, how you find the derivatives of rational expressions like this or rational functions. But hopefully you can see what you can do here. Because I just have an x squared down here, I can break this up. This is t cubed over t squared minus 2t squared all over t squared plus 7 over t squared. Now look how easily this simplifies. T cubed divided by t squared is just t. The t squared is minus out, or cancel out, excuse me, minus 2. And then this becomes plus 7 t to the negative 2. So then f prime of t, well, what's the derivative of t? Well, that's just 1. All right, the derivative of a constant is 0, so that goes away. And then bring the negative down. So plus 7 times negative 2 t to the minus 2 minus 1. Well, 1 minus 0 is 1. 7 times minus 2 gets me minus 14 t to the minus 3. So again, even something like this, just figure out how you can best rewrite it to tackle the problem. Like that's the key to tackling this one here. Okay. Now let's talk about some trigonometric functions. So So we know there's 6 basic trigonometric functions. So this lecture here, we're just going to talk about derivatives of sine and cosine. In the next lecture, we'll talk about, tangent, cotangent, secant, and cosecant. Okay, but so this one here, the derivative with respect to x of sine of x, this is convenient, is just cosine of x. And then the derivative with respect to x of cosine of x is just minus sine of x. So look, the proof for this is in the text. So I'm going to do this proof for you, be like, well, that's really convenient that the derivative of cosine of x is minus sine of x. So always remember this. Derivative of sine of x is cosine of x. Derivative of cosine of x is minus sine of x. So it's really important to remember this negative, okay? You would think that they would just flip-flop like this, but whenever you take the derivative of cosine of x, all right, the derivative is actually equal to negative sine of x. All right, so let me prove that to you. Okay, so do an informal proof on the next slide. So we're going to do a proof that the derivative with respect to x of cosine of x is equal to minus sine of x. And to do that, what we're going to have to do is we're going to have to recall a few things, okay? You have to recall that the limit as delta x goes to 0, all right, of cosine of delta x minus 1 over delta x. We did this as just x, but it doesn't matter if instead of x we call it delta x. Okay, this is equal to 0. And that the limit as delta x goes to 0 of sine of delta x all over delta x, that's going to be equal to 1. And then we're going to need a trig identity here. Okay, cosine of alpha plus beta, that's cosine of alpha times cosine of beta minus sine of alpha sine of beta. So what we're going to do is we're actually going to use the limit definition. Okay, so the derivative with respect to x of cosine of x, well, that's equal to the limit as delta x goes to 0 a cosine of x plus delta x, that's f of x plus delta x, minus f of x, well, that's just cosine of x, right, all over delta x. So look, you can see we're going to use this trig identity, right? Cosine of alpha plus beta. Well, x is my alpha, beta is my delta x. So this is the limit as delta x goes to 0. So this is cosine of x, cosine of delta x, minus sine of x, sine of delta x. And then don't forget you have this minus cosine of x all over delta x. Well, look, you're just going to rearrange some terms here, okay? Watch this. You're going to move this cosine over to here, okay? So this is limit delta x goes to 0 of cosine of x, cosine delta x, minus cosine of x. I'm going to put this all over delta x, minus this sine of x, sine of delta x, all over delta x. I just moved the cosine over here and broke it up a little bit. Well, look what's going on here. Do you notice how I have a cosine of x here? Let me just factor that out. All right, so that's the limit as delta x goes to 0 of cosine of delta x minus 1 all over delta x times cosine of x minus, now I'm just going to move this sign out, sine of delta x over delta x times sine of x. Well, look, I'm only interested as delta x goes to 0. Well, look, cosine of delta x minus 1 over delta x, that's 0, okay, as delta x goes to 0. So that's 0. Cosine of x is just cosine of x. There's no delta x in it, so we're going to leave that alone. And then look, the limit as delta x goes to 0 of sine of delta x over x, that's 1. And then I have a sine of x. Well, look, 0 times cosine of x, that goes away. And I'm just left with minus sine of x, which is what we said we should get. So the proof of the, just to go back real quick, the proof of this in the textbook is very similar. Okay, it's almost exactly the same. So I encourage you to look at that one too. But here's the important thing. You got to always remember these, okay? This is just something that you need to like put in your brain, to memorize. All right, so let's do some examples, okay? Let me get this one out first, and then we'll do some examples of trig and this. So next, the derivative of the natural exponential function, okay? So it turns out the derivative of e to the x, this is really simple, is just e to the x. So this is very simple. Note, okay, this only works for e to the x, okay? So if we have the derivative with respect to x of e to the 2x, that is not equal to e to the 2x. It's actually going to be equal to 2e to the 2x. We'll talk about that when we learn about a rule called the chain rule. Okay, so it needs to just be e to the x. Okay, anything other than an x up here, it doesn't work. All right, so let's do some examples. All right, so just always remember, derivative of sine is cosine. The derivative with respect to x of cosine of x, that's equal to minus sine of x. And then this derivative with respect to x of e to the x is just e to the x. All right, so let's find the derivative of this first, okay? And for these examples, find f prime of the following. So let's look at f of x is equal to 5 times sine of x minus 2 cosine of x plus 3 e to the x. Well, look, f prime of x. Constant, just leave the constant there, so that's 5. The derivative of sine, boom, is cosine of x. Minus 2. Well, what is the derivative of cosine? It's minus sine, so this becomes plus sine of x. And then plus 3, and the derivative of e to the x is just e to the x. We got it. Let's try this one. F of x is equal to the 5th root of x squared plus 1/2 e to the x plus 2 sine of x plus 5. Well, look, this you're just going to write as x to the 2/5. So then f prime of x, you're going to bring the 2/5 down. So 2/5 x. 2/5 minus 1 gets me minus 3/5. Derivative of e to the x, so this is just plus 1/2 e to the x, got that. And then look, what's the derivative of sine? It's cosine. Plus 2 cosine of x. And the derivative of 5 is just 0, so that just goes away. So these derivatives of sine and cosine and the natural exponential function, it's pretty straightforward once you just remember, like right off the top of your head, what these derivatives are. All right, let's try this one. Let's look at f of x is equal to pi cosine of x minus pi sine of x. So f prime of x, well, pi is just a constant. What is the derivative of cosine? Boom, it's minus sine. So this is minus sine of x minus pi, and then the derivative of sine, boom, cosine. We got it. Let's do this last one. F of theta is equal to 4 sine of theta and then minus theta. Oh, so I'm sorry, f of x, or f of theta, excuse me. So f prime of theta. Well, this is 4. Derivative of sine is cosine, so this is cosine of theta. And then theta here, well, what is the exponent? It's just a 1, so bring the 1 down. And then you get 1 minus 1 is 0, so it's just the derivative of just x, or in this case just theta, is just 1, right there. We got it. All right, let's do 2 more. Let's try this one. Let's find the slope of the function. So our function here is f of t is equal to 2 minus 4 over t, excuse me, at the point 4, 1. Okay, so I want to find the slope of this function at the point 4, 1. All right, so to find the slope, what gives the slope of a function, right, at a given point? That's the derivative. So first you need to do is find f prime of t. So I'm going to need to rewrite this. F of t is equal to 2 minus 4 t to the minus 1. So f prime of t, well, derivative of a constant, boom, goes away. This is 0. So bring minus 4, bring the exponent down, minus 1. T, all right, to the minus 1 minus 1. So in this case, negative is a positive. So 4t to the minus 2. So this is just 4 over t squared. So I want to find the slope at this point. So the slope at 4, 1 is equal to f prime evaluated at 4. So I'm just going to take my 4, plug it into my derivative. So this is 4 over 16, or the slope of the tangent line, right, at that function, which is the slope of the graph at that function. It's the instantaneous rate of change at the point 4, 1 is just 1/4. All right, let's do a crazy one. Okay, let's do a crazy one that's going to involve a lot of silly algebra here. All right, so this will be our last example. Let's find the equation of the tangent line to the graph of, okay, so our graph is h of t is equal to sine of t plus 1/2 e to the t. So at the point, and our point here is going to be pi 1/2 e to the pi. Oof. All right. So I want to find the equation of the tangent line. So the first thing I'm going to need is the slope of the tangent line. Okay, so the slope of the tangent line is going to be found, okay, by finding the derivative. So h prime of t. All right, so the derivative of sine is cosine, so that's cosine of t. Derivative of e to the t is just e to the t. So plus 1/2 e to the t. So next, to find the slope, is going to be h prime, and I'm literally going to plug in pi. So, well, that's cosine of pi plus 1/2 e to the pi. All right, well, what's cosine of pi, right? Cosine of pi is -1. So that's -1 plus 1/2 e to the pi, which I'm just going to write as 1/2 e to the pi minus 1. All right, so that's my slope, okay? So next what we're going to use, we're going to literally use point slope to find the equation of the tangent line. So it's y minus y1 is equal to m times x minus x1. All right, this is my point over here. So this is y minus 1/2 e to the pi is equal to my slope, which is this, 1/2 e to the pi minus 1 times x, and my x value is pi, minus pi. All right, you have to distribute the slope. So this is y minus 1/2 e to the pi is equal to, when I distribute the slope to the x value, I'm going to leave it in parentheses. 1/2 e to the pi minus 1 times x. Now I'm going to distribute it to the constant. So this is, don't forget the minus, so this is minus pi over 2 e to the pi, minus becomes plus pi. Now literally you're just going to add this over. So this is y is equal to 1/2 e to the pi minus 1 times x. And then I'm adding this over. So I'm actually going to put it in front. Plus 1/2 e to the pi minus pi over 2 e to the pi plus pi. So this is my slope, and this is crazy, but this whole thing here is my y-intercept. So it's not that it's hard here, it's just that there's a lot of moving pieces here for you. All right, class. We're going to get a chance to continue to practice these rules. You're going to see them in every lecture going forward. But I hope all these examples kind of helped illustrate these rules for you and gave you a pretty good understanding of them. As always, I'm here if you need anything.